And now, let's start. Our topic today, the basic building blocks of color. Today's agenda, basic color theory with answering the question, how we perceive color, how are illuminants and standard observers defined, what are the different types and how do they differ. We'll talk then about the interaction between light and object. And last but not least, we'll have a closer look on the geometries of a spectrophotometer. What are the differences and which geometry is recommended for which application? We perceive uniform and consistent color as high quality. It means color harmony plays a major role as it influences our buying decision. Many finished products are, as those of our pictures here, consist of multiple components. And most of the time, these components are manufactured by different suppliers at different locations. But in the end, the assembled product should be uniform in color. A uniform look and feel is a big challenge for the complete supply chain. But what does it mean that an instrumental color QC is necessary then? Our color perception is subjective, means it is depending on our mood, gender, and age. The second thing is that we are not able to communicate nor to remember colors. Color is also dependent on the background. That's why, for example, we use standardized light booths to evaluate colors. And also color is dependent on the surrounding light. Due to the big disadvantages of visual color perception, objective methods for evaluation of color are necessary, means that objective instruments with international specified color systems are required. Let me show you some examples. Here you see how the gender influences our color perception. Researchers from Arizona State University have determined that there is a gene that allows us to see the color red. Because this gene sits on the X chromosome, and we women have 2 X chromosomes, means 2 copies compared with only 1 for men, the gene aids women's ability to perceive the red-orange color spectrum. Women are able to differentiate the colors, especially red, by their hue, crimson, burgundy, and tomato red, while men see just red. With this example, I want to show you how bad we are in remembering colors. Here you see different tones of blue, and I would like you to have a closer look on this one and memorize it. Which one was it? Make a guess. Did you choose the right one? There is a yeah. Great. I have to say, for me, there are so many similar that usually I think it's this one. So it's not so easy for sure. Okay, here again our different hues of blue, but now they're named. And now I would like you to focus on these two, the B22 and B23. How would you explain the differences between these two blue colors? Difficult. Homebush blue this Australian beach is beautiful for sure. You see, we're not really able to communicate nor to remember colors. This is an example how colors can be impacted by the surrounding area. The small pink squares in the center of each block on the left side are the same color. Different background colors make them appear to be four different colors. And the same optical illusion occurs with the green squares in the center of the blocks on the right side. So, you see, it's truly the same color. When we remove the backgrounds and replace it with a neutral gray color, the color of the square is the same. That's why all whiteboards are made in a neutral gray color. Furthermore, this gray is also defined in international standards. Hope you agree, we truly need objective numbers. Fortunately, we can use objective methods that define how to communicate colors. Several international standards organizations like DIN, ISO, ASTM, CIE have specified and standardized the procedure values, for example, the C-lab system and spectrophotometers. Which building blocks are needed for an instrumental color measurement? This is what we see next. For color perception, three elements are needed. The object itself with its specific color, a light source, because without light we cannot see anything, and an observer. Without an observer, there would be no color. In the following, we will speak about all three elements separately, starting with the light or illuminant. When white light is bent using a prism or grating, it can be refracted into all visible colors, beginning with blue and ending with red, like the rainbow. The refracted white light is expressed in terms of the length unit nanometers, where blue starts at 400 nanometers and red ends at 700 nanometers. Below 400 nanometers, the UV light is starting, which is used to see optical brighteners, for example, in paper or textiles. They create a whiter than white look. Above 700 nanometers, infrared light starts. It is used in many technical applications, for example, to create heat, or also for some military applications. Color changes with light source. Due to that, different illuminants are defined by their spectral powder distribution, means by the amount of emitted energy at each wavelength. Here you see the spectral power distribution of this standard illuminants. These are actually the three most important standard illuminants. D65, D stands for daylight, 65 for the color temperature of 6,500 Kelvin. D65 has the same amount of energy over the whole spectrum, what you can see here. Almost the same amount of energy everywhere. This means it is nearly white light and all colors appear bright. A is the tungsten lamp. You can see that the emitted energy in the red area of the spectrum is very high. And accordingly, it is a more reddish light with a warm atmosphere. And F2 or also F11 is a very common fluorescent light. So F stands for fluorescent. There are different F light sources, but especially on your side of the planet, F2 is still the most common lighting used in stores and offices. Compared to D65 or A, fluorescent light has no smooth curve, but peaks at specific wavelengths. Mostly, it is a more greenish or bluish light because these peaks are usually in the blue or green area. For sure, also interesting would be the LEDs. However, they are still not defined as standard illuminants, so I cannot give you any details on this. But still, you're wondering maybe, why do we need standardized illuminants? Well, I already mentioned color changes with the light source. And as an example, your laptop is consisting of different components, and they all shall look the same, no matter if you are working in the office, outside, or at home under tungsten lamp. That's why it is important to evaluate the color under different illuminants. Here you see another example, these blue samples. Why do the samples here look the same under daylight, but different under tungsten lamp? This phenomenon is called metamerism. Metamerism can be a serious problem for manufacturers, especially for those who combine various parts of different materials or sources into one product, as the laptop. As a result of this phenomenon, the Metamerism index, MI, has been developed. The MI is a single number index that indicates how well two samples that match under one illuminant will match under another illuminant. Usually, the 65 illuminant, so daylight, is used as the reference illuminant. So, if when these samples are matching under daylight, how good will they match also under illuminant A? And if you have a value that is MI value that is lower than 1, then everything is fine. But if the value is higher than 1, you probably have a metamerism problem. Another rule of thumb is if you check the reflectance curves, if they're crossing each other at least 3 times, like you can see it here, this is an indication that metamerism is present. Okay, this was the light source or the illuminant. Now I want to have a closer look on the observer. Maybe you've heard the expression 2-degree or 10-degree standard observer already. We'll go deeper into the theory, what's behind this definition. The color of an object that we see is determined by 3 components, a physical one, a physiological one, and a psychological one. The physical component is a combination of the start of the illumination and the reflectance of the object. Light is falling on the eye. The physiological part of our vision is based on the electrochemical processes of the eye. As a result, the eye sends electrical impulses through the optic nerve onto the brain. As a conclusion, our brain creates the image we see, and that's where the psychological component comes in. Our brain adds meaning to the received signal based on the context, our experience, and memory. Means our brain actively interprets and changes what we see. So color is an impression and is as subjective as tasting, feeling, hearing. And now a short excursion into biology. The eye contains two types of receptors, cones for color detection and rods for light-dark detection. The cone cells are consisting of three types, one that reacts to red light, one to green, and one to blue light. The combination of them simulates the brain to produce the impression of a specific color. And on a special small spot of the eye called foveum, only cone cells are present, no rods. That's why some scientists in the 1930s figured out an experiment based on that. They used especially this area where we have the cones. And this is the experiment. It was conducted to find out how sensitive these three different cone cells are. Several test persons were looking at a white background, so this is here the white background, through an aperture having a 2-degree visual field. So this is the opening, this is the aperture. The bottom half of the screen was illuminated by a colored test light, and the observer then adjusted the intensity of the three primary colored lights, red, green, and blue, mixing together on the top of the screen until they matched the color shown on the bottom half. And this process was repeated for test lights covering the entire spectrum of visible light. So again, why did they choose the 2-degree field of view? As I mentioned, because of these small spots on our retina, because of the foveum, and because there are only cones or only color receptors located. So this represents the 2-degree field of view. What's also important is that we have the distance of about 50 centimeters to the samples. What does it mean? It means that we look on an area that is with the size of a small coin. So when the initial tests were done to describe the color in terms of light mixing, this 2-degree field of view was used for the observers to look through because, yes, the scientists thought this will be the perfect area, the best for color perception. And that's why they defined the 2-degree standard observer. But you know, in practice, the observed samples from a distance of half a meter are usually larger than a small coin. And the color perception is not only influenced by the color receptors, but also by the lightness detectors. So in the 1960s, a second experiment was conducted using an aperture with a 10-degree field of view. So with the area that evaluating area that is as big as a tennis ball. And this is how we receive the 10-degree standard observer. What does this mean? Well, the 2-degree standard observer does not correspond with color viewing, especially because the color perception is influenced by cones and rods. As a result, the 10-degree standard observer was established as it corresponds much better to the visual perception. The definition of the 2-degree and 10-degree standard observer are standardized, as you see here with all these curves, and published in international standards. These values are all stored in the spectrophotometers. They're used in the background. What you can choose is 2-degree or 10-degree standard observer. Why do we still have the old version, the 2-degree? Because there are still other standards that are based on these definitions, and they've never been changed. So if you want to work according to some standards, then you have to take the 2-degree standard observer. However, our clear recommendation, if you have the choice, then please take at any time always the 10-degree standard observer. Then it really responds better to the visual perception of the human eye. Okay, we had the light source and the observer. Now we're coming to the object itself. What can happen to the light illuminating an object? Here you see the gloss. The incident light is directly reflected on the surface, means only in the main direction of reflection. The angle of incidence is equal to the angle of reflection. Approximately 4% of the incident light is spectral reflectance. The remaining light penetrates the sample and interacts with the sample pigments and other compounds. Here you can see the absorption. It changed the intensity of the light of individual wavelengths. Absorption contributes primarily to the color of the object. So colorants have a specific absorption spectrum. And this is the diffusion. It leads to diffuse reflection of light from the inside of the object. Diffusion contributes mainly to the hiding power. But of course, none of these effects occurs alone. It is always a mixture. So let's have a closer look at the combination of this phenomenon. When light strikes an opaque sample, there are two types of reflectance on the surface. On the one hand, the specular reflectance or gloss, and the color of this light is white. And on the other hand, the diffuse reflectance, the color itself. Pigments and dyes selectively absorb some wavelengths of light while scattering other wavelengths. We see here the color orange because all the other wavelengths of the white light have been absorbed. Only the yellow-red wavelengths remain to be seen. Why is the light diffusely reflected? Because of the irregular surface shape of the pigments. Which percentage of the light is reflected directly or diffusely is dependent on the surface texture. As a result, the surface texture of an object is always influencing the color. How an instrument determines the color of an object? The optical properties of the object are measured with a spectrophotometer. It simply determines the complete amount of light that is reflected by the object at different wavelengths. This reflectance curve shows the spectral data and acts as a fingerprint for the object colors. Here you see 4 different spectral curves of 4 different colors, but we'll come back to them again. First, black, for example, means a zero reflection, so no light is reflected. You would have a curve that is only on the bottom. And exactly the opposite for white, there all the light is reflected. All other colors reflect only in selected parts of the spectrum, as this example here. So let's come back to them. We play again a guessing game. Which color do you think is behind this picture here? It's a blue. Blue light is reflected and nearly all green, yellow, and red light is absorbed. So the upper right corner, it's a red. Left bottom side, it's a green. The green light is reflected and nearly all blue, yellow, and red light is absorbed. And last but not least, the right bottom side, our most difficult example. What is it? It's a yellow. As you see, the yellow is a mixture of several wavelengths. And as it's a quite bright color, you almost everywhere have a high amount of reflection. Okay, I assume you agree that comparison of spectral curves would be a lot of work in the daily business. So what's to do? Because it's too hard always to compare the spectral curves, the color systems were developed. The 3 elements, standard illuminant, standard observer, and the spectral data of the object are combined and converted into the color systems. The color systems are tools for documentation and communication of color and color differences. The system which is recommended by the CIE for solid color is the CLAB system. Compared to the spectral data, it is very easy in handling as only 3 values are calculated. So let's have a look on that. Here it is, the CLAB system. It's developed by CIE, Commission Internationale de l'Éclairage, the International Commission on Illumination, and it describes all the colors visible to the human eye. It is also the most common color system nowadays, so I'm quite sure you know it, you use it in your everyday life, in your everyday work. It consists in total of 3 axes. A star, B star are the 2 axes that represent the hue dimension of the color. They are at right angle to each other. And the 3rd axis is the lightness, L star. It is perpendicular to the AB plane. In this system, any color can be specified with the coordinates L, A, and B. But keep in mind, color measurement is always a comparative measurement, means a sample compared to a standard. So we compare color differences, delta L, delta A, delta B. So let's see an example. Here is the standard. And here is the sample. Now, the differences for every single axis are calculated. Delta L, delta A, delta B. And the calculation is always sample values minus standard values. For those who think that 3 values are still too much, the delta E star value can be calculated. Delta E star is only a single number which describes the total color difference between these two colors. Here you can see a typical measurement report where all the data is displayed. Now we have talked about all the basics. You see the illuminant, the standard observer, our object, it's a black sample we have here. And what else? Yes, the color systems, the delta E with the C-lab system, you can see here. So what's missing? The measurement geometry. In the industry, there are two classes of instruments used to measure color. 450, as you see here, and the sphere geometry. But before we can decide which geometry we want to use, we need to figure out what we want to measure and which result is interesting for us. So let's have a look on some samples. Here, these two. It's a black one and a red one. Black is an achromatic color, while red is a chromatic color. So you can also see that one half is coated with a clear coat, appearing glossy, while the other part appears matte. With both parts having the same pigmentation, you will notice that the glossy part looks darker and more saturated than the uncoated part. What's the conclusion? Both color and gloss are influencing the visual perception. So let's have a short look at the gloss theory first, and then we go further with our samples. On a smooth and highly polished surface, an image can be observed distinctly. The incident light is directly reflected on the surface, means only in the main direction of reflection. The angle of incidence is equal to the angle of reflection. The more direct light is reflected, the more obvious will be the impression of gloss. On a rough surface, less or none of the light is specularly reflected. A reflected object does no longer appear brilliant, but blurred. Most of the light is diffusely scattered into all directions, so the image-forming qualities are reduced. The more uniform the light is scattered, the less intense is the reflection in the main direction, and the duller the surface will appear. So, now we go back to the geometries. The first geometry I would like to show you is the 450 geometry. As you can see here at the picture, the 450 geometry uses a 45-degree illumination, and it is a circumferential illumination. And at 0 degree, we have the detector perpendicular to the sample plane. This simulates visual color evaluation by excluding the gloss. For example, when we look at a glossy part, we position it in a direction which avoids gloss hitting our eyes. The same way as when we are reading. We have already seen before, a high gloss sample with the same pigmentation is visually judged darker by the eye when compared to a matte or structured sample. This is exactly what a 450 geometry measures. Differences in gloss and texture lead to color differences. Some typical applications where it is necessary to have the agreement with the visual assessment are comparison of a sample to a standard, batch-to-batch comparison, and assembly of multi-component products using different materials. A good example are car interior parts, which have to be harmonized. Furthermore, the advantage of circumferential illumination is to achieve more repeatable measurement results on directional structured surfaces. Means no matter how you position the device, the result shall be very similar. Now, how does the D8 geometry work? The D stands for diffuse or sphere. So there is no direct illumination anymore. It's a diffuse illumination. The sphere geometry illuminates the sample diffusely by means of a white coated integrating sphere. Baffles prevent the light from directly illuminating the sample surface. The measurement is done using an 8-degree viewing angle. So the detector is at 8 degrees here. The D8 geometry consists of two modes. The first one, the spin mode, specular included, where the total reflected light is measured, means the diffuse reflection, the color, plus the direct reflection, the gloss. Instruments with this geometry do not differentiate whether the surface is glossy or matte or structured. They simply measure all reflectance coming from the object. A sphere spin color instrument is used in situations where color change is primarily influenced by the object's colorants, for example, pigments or dyes. Typical applications are color matching, color strand development, or weathering studies. So a raw material supplier of pigments or resins, for example, would use the sphere spin geometry to check lot-to-lot consistency. But again, please keep in mind, this geometry does not correlate with the human color vision. Then the second mode with the sphere geometry is the specular excluded mode, where a gloss trap is used to capture directly reflected light, so the gloss is trapped. This configuration partially simulates measurement with the 45-0 geometry. On high gloss samples, where the incident light is directly reflected, the correlation to the 45-0 geometry is good. In case of medium or low gloss samples, deviations will occur between the 45-0 and the specs configuration, as the gloss trap does not completely exclude the specular component. As a result, the sphere specs geometry is only recommended for high gloss and non-structured materials, because here the correlation to the 45-0 geometry is given. So the idea is you would have the spectrophotometer with the sphere geometry, and then you can switch between the spin and specs mode, so you have two devices in one. However, you only have a simulation of the 45-0 geometry, so you have to pay attention if the values that you receive make sense or not. But anyways, a lot of theory, so let me show now how this looks in practice. Here, our black sample, it's measured, and you can see the values with all the three different geometries. A color instrument with 45 geometry measures the way we observe the color. So we have dark black and matte lighter black that is more gray maybe. So that difference mainly results from the difference in the L value, in the lightness, because we perceive samples with lower gloss as lighter. A and B are hardly visible. They're here, and there is no difference, and they're not affected. Yes, for sure. It's a black means an achromatic color. As the two samples don't look the same due to the different gloss level, the 45-0 geometry measures a delta L of round about 12 units. So this is the difference from 10 to 22. A color instrument with an integrated sphere geometry, specular included, this measurement here, is not influenced by gloss or texture. So for these two samples, the instrument measures no color difference for the two gloss levels. Also, the delta E will be round about 0. And now the sphere specs geometry. Specs gives the same result like 45-0, but be careful, the values are different. Especially here, this one, you see, it's 26 is quite high in comparison to this value here. Okay, as a small summary, the visual perception of colors is influenced by gloss and sample structure. Two sides of a sample with same color hue, however with different gloss or structure, appear visually different, as we see on the picture. This corresponds to the measurement geometries 45-0 and sphere specs, and does not correspond to the sphere spin geometry. Okay, and now the same for our chromatic red. Also, with the red samples, the visual perception is influenced by gloss and structure. So we see it clearly in the picture. The two samples measured with 45-0 and D8 specs show differences however, not only in the L value, but also in the A and B value. So you can compare the blue to the orange numbers. You see that there is a difference. So there is a difference between the glossy sample and the matte sample. The color hue of the glossy side is perceived as darker, so lower L value, okay, but also as richer, deeper color. So the colors are more intense, stronger, and this is what you see also in the values. So we see the higher A value and the higher B value when we compare the glossy part to the matte sample. And once again, the correlation between the 45-0 geometry and the sphere specs geometry is very good. So here, basically, when you compare 45-0 to sphere specs, you see there is no difference, almost no difference at all. So as expected for the sphere spin geometry, these measurements here, there are no significant differences between glossy and matte parts again. And all these measurements were fulfilled with our spectrophotometer that I would like to show you shortly, the Spectral 2 guide. For color measurement, you can choose the geometry is 45-0 or sphere spin specs is 2-in-1. Additionally, there is gloss meter built in, so you will have two real devices in one, color and gloss measurement. And here you can see an overview over the whole Spectral 2 Guide family. For sure, a lot of you already know our first generation Spectral Guide, this one here. And this is its successor, the Spectral 2 Guide. We have two designs for the Spectral 2 Guide family, the Spectral 2 Go and the Spectral 2 Guide. The second generation has some great advantages compared to the first generation. And the one advantage is the possibility to using digital standards, as digital standards can only be used when the technical performance, in detail, the reproducibility is excellent. Furthermore, our Spectral 2 Guide Standard Plus design is able to combine 3 devices in one. Additionally to color and gloss measurement, the worldwide smallest fluorimeter is built in the instrument. This fluorimeter is able to detect fluorescence and additionally gives you a prediction how colors may look like when all fluorescent pigments are decayed. So, information about the color stability. The Spectral 2 Guide Pro combines these 3 instruments in one, plus it is able to measure very deep and dark black colors, the so-called jetness. So once again, this is only possible because of the extreme precision of the instrument. So that's all what we prepared for you today. Now it's time for your questions. And now you have, again, a few minutes time also to write down and for me to read the questions. And in the meanwhile, I will give you a short introduction of some of my colleagues. So if you have any questions now or later concerning application, webinars, seminars, or general information about our instrument, here are the people that are happy to and will be pleased to be in assistance to you. Here you can see me with my contact details. 5 of us are located in the headquarters here in Germany, next to Munich. And then we also have our technical service team in the US, Corey Cohen, our application specialist, as well as James Fasco, our product manager for physical testing equipment. Feel free to join us with our next webinar. This would be the next place where we can meet each other. It's the color control and new prediction of color stability. So this is today's topic where we go much more in detail, especially about fluorescence. So how is measured color and gloss, you can see in detail, and also what is fluorescence and how can it be measured, how we predict color fading with the new indices delta FL and delta E0. So if you want to know more, please feel free to join this upcoming web seminar on 24th and 25th this month. Then we offer also customized on-site seminars. Nowadays, in these days, what means on-site seminars? We would be happy to visit you, but of course, we can do it also online. So just get in touch with us and we can customize some seminars for you. And also you are warmly welcome to visit our webpage as well as our YouTube channel, where you can find more information about our products how to do videos with technical details and application details, technical articles, and many, many more. And last but not least, the most favorite meeting point is our headquarters in Geretsried. So if you're interested to see how Big Gardener production site is working and where it is located, you're warmly welcome. And once you're here, don't miss to visit the beautiful countryside of Bavaria and Munich. And now, again, come back to your questions. So I need a moment to have a look. A short hint. Again, you will receive the slides of the presentation with the email in the next days. And also, you can have this recording from the web seminar. You can find it at the same place where you fulfilled the registration form for the web seminar. In the next days, there will be a new link with the recording. I'm reading your questions at the moment. We're so many today. If I'm not able to answer all of them, I will come back to you via email, okay? Here is, for example, a question about LED light. As I mentioned, there are so many, it's like with the fluorescent tubes, you have so many combinations. And with LEDs, especially as they are not standardized at all, you can have a combination of, you can have white LEDs of all the different generations they had, or also a combination of blue and yellow LED, or here it's a full spectrum LED named. So as long as the light spectrum curve is close to natural light, it should be acceptable for color checks. Is this right? And for this, I would like to go to the right slide. Let me check. Where is it? Here. So when you have the LEDs, you have something similar like these spikes, but they're wider. So you will have something like this. So, and in the best perfect case, maybe you will be able to fulfill exactly this curve. But it's never possible to have 100% covering. So it's always a simulation. There is no light source that is fulfilling the daylight standard illuminant. This is really a challenge to receive a light source that is exactly as good as the light outside. Of course, the problem with the natural daylight is that it changes with the time of the day, with the seasons, with the weather outside. So to have a stable daylight illuminant is really a challenge. It doesn't matter with which light source you try to simulate it. here are some questions. I see some of you are using multi-angle spectrophotometers for effect pigments or for effect finishes. For this topic, we have a special webinar because color measurement of effects is really some theory on its own, and it's another world, so to say. And the same way with the question about delta E star or delta E CMC. So with all the different color equations, also there we have a special web seminar for the different color equations. For sure, there you will receive all the information you would need. Here, this is the basic web seminar, and it would be a bit too much to start with this now. Okay. So I'm checking again. Here it's a good question. What about the samples? Do they need to be always flat? So do we need always a flat surface? What to do with small samples? The most important is that you compare the same. So standard and sample should be as flat as possible. But if they are not completely flat, then they should have the same curvature. Then you can compare the measurement data. What's of course the most important thing is the aperture. So the opening at the instrument should be closed. So if you have, you can see it here also with the details of the instrument. So as you can see here, when you have the aperture size 11 or 12 millimeters, so you need at least a sample that is 12 millimeters or 11 millimeters big. Okay. Is there another beetroot to measure metamerism? You definitely need a spectrophotometer to measure, to have a metamerism index, because you really need the differences between the spectral curves. If you have no, like, if you just have a color meter, then you have no spectral curve, and then you cannot receive any data, as you can see here. Okay, we are actually over the time. Maybe I will try to find one last question. It's really nice to read here from all the different countries in the world. There are so many feedbacks. So please really feel free also to contact me later, to write an email, and I'm happy to answer your questions, also to go more deeper in detail with all the other questions you have, not only on this topic. Okay, as we're here with the metamerism, I will finish today's web seminar with the question how to fix the metamerism. So what to do to avoid metamerism, or how to understand metamerism and how to fix it. For this, you have to understand why we have metamerism. We have metamerism always when we have different pigmentations or different pigments. And this happens easily when you use different coatings, for example, for different substrates. When you have textile and leather and metal substrate and they're all coated, then you use different coatings and automatically different pigments to reach the same color. So there you can expect to have metamerism. And then if you want to fix it, then you should check the reflectance curves of the pigments, that they're as equal as possible. So that's it. Now it's the time to say goodbye for today. Thank you for your rich participation, so many people today here. I hope to meet you very, very soon again, and wish you a very nice day. Bye-bye.